going at a constant speed of roughly 25 miles per hour. When I throw this ball up, it's going to land exactly where it was. So now I'm going to accelerate and the ball is going to fly behind me.
As shown in the diagram, when the car is moving at a constant velocity of 30 miles per hour and doesn't accelerate, and the ball is thrown in the air, the ball also moves at 30 miles per hour and can therefore land back to its starting position in Ryan's hand when thrown up in the air. However, when the ball is thrown up in the air when the car has a starting velocity of 30 miles per hour, but then accelerates to a velocity of 40 miles per hour while the ball is still in the air, the ball has already reached its peak height and is only moving the initial velocity of the car, which is 30 miles per hour. Therefore, since the ball is moving slower than the car while it's in the air, the ball appears to move backwards. However, it is actually the car moving forward because of its greater velocity.
Go. Go ahead.
While in the situation in which Kareem and Will both began with an initial velocity, upon collision the forces exerted between the two of them were unbalanced, causing there to be a net force, better known as F-net. As a result, Kareem and Will felt different amounts of force exerted between the two of them after collision, as compared to when Kareem was motionless and Kareem and Will experienced the same amount of force upon collision, except in opposite directions. As shown in our demonstration and diagrams, when Will and Kareem collided with one another while Kareem was motionless and Will had an initial velocity, both Kareem and Will felt the same amount of force of the collision due to Newton's third law, except they felt it in the opposite directions of which they were facing upon collision. However, the physical effect of the forces exerted on Kareem and Will differ due to the different forces of gravity and exerted forces upon each of them.
Go ahead, Ben.
As shown in our diagrams and video, when trying to catch a football without cradling it, the impact time is much shorter, causing the same amount of energy to be transferred from a football to a person's hands as when the ball is cradled, but in a much shorter amount of time. Also, the change in momentum of the ball from having momentum to having no momentum is much faster when the ball is not cradled as opposed to when it is cradled because of its shorter period of time of energy being transferred from the ball to the catcher's hands. As a result of the change in momentum and transfer of energy in such a short amount of time, the net force of the ball experienced by the hands of the person catching the football feels greater because of the same transfer of energy, but in a shorter period of time. However, when cradling a football while it is being caught, the energy transferred from the football to the person catching the football's hands is the same as in the scenario where the football is not being cradled, except the period of time the energy is being transferred is longer. The change in momentum of the football from having momentum to having no momentum is also a greater period of time compared to when a football is being caught without cradling it. As a result of the longer period of time for the change in momentum and transfer of energy of the football when cradling it, the force of the ball experienced by the hands of the person catching the football feels much less than when catching a football without cradling it, because the same amount of energy is transferred over a longer period of time.
Record it. Here, yeah. Record one regularly, and then can you switch to slow-mo afterwards?
Yeah.
Okay. Ready? You ready now?
Yeah.
That's my bad. Yeah, go ahead, Ben. Go ahead.
a meal.